Thanks for tuning into the FORC talk on outcome indistinguishability. In this work, we revisit the underlying goals of individual risk prediction. So typically, the goal of individual risk prediction is framed as finding a best fit hypothesis. For instance, in the agnostic pack model, the goal is formalized by first fixing a hypothesis class, then learning a hypothesis H that achieves loss, in this case squared loss, that competes with the best hypothesis in the class. While this framework has been wildly successful for learning accurate predictors in diverse domains, a critical downside of the pack framework is that it only considers the overall performance, not where these errors might occur, which can lead to downstream unfairness. So in this work, we propose a new paradigm for learning, outcome indistinguishability, that frames the goal of learning as finding a model that in some sense is indistinguishable from the true outcome model, which we'll call nature. To understand this goal, consider the following challenge. On the left, we'll take an individual outcome sample, either from nature or from our model of nature. Then we'll pass this sample to a distinguisher. The distinguisher's job is to guess whether the individual outcome pair came from nature or from the model of nature. Our goal will be to develop a model where the distinguisher can't succeed much better than random guessing. More formally, we assume that nature is a joint distribution over individual outcome pairs, but make no further assumptions. For the model of nature, we observe that any predictor, p tilde, suggests a generative model for outcomes. In this distribution, we sample an individual x from nature, then resample their outcome according to the Bernoulli distribution with parameter p tilde effects. With this notation in place, we can restate our goal to learn a predictor p tilde whose modeled distribution, dp tilde, is indistinguishable from nature's distribution. The question we have to ask ourselves then is indistinguishable to whom? If we allow any distinguisher, then it's not hard to see that the modeled distribution must be statistically close to nature, which is impossible from a small sample. Thus, to have any hope of achieving the goal, we need to consider a computational relaxation. So this leads us to the formal definition of the OI framework. First, we fix some bounded class of distinguisher algorithms, A. These algorithms will map individual outcome prediction triples to 0, 1. Then we say that a predictor is A epsilon OI if, for all algorithms in the class, the probability that the distinguisher returns 1 on samples from nature and samples from the model are within epsilon of one another. Note that in both cases, we only allow the distinguisher to look at the prediction according to p tilde, to the model, not according to nature. So in the paper, we explore variants of this OI definition, studying their properties as learning desiderata. And so one of our main results actually connects OI to multi-calibration. We show that outcome indistinguishability essentially encodes the same requirements as multi-calibration, which is a notion that's been studied in the context of fair prediction that aims to ensure predictions are calibrated across computationally identifiable subpopulations. And so by this equivalence, I mean it in the sense that for any class of subpopulations, I can construct a class of distinguishers, A, such that AOI enforces this C multi-calibration, and vice versa. So finally, the OI framework allows us to actually go beyond the multi-calibration framework by introducing different models of distinguishers. And another key result investigates a model of OI where we allow the distinguishers oracle access to the predictive model P tilde. We show that this variant of OI is strictly stronger than multi-calibration. In other words, query access actually allows these distinguishers to run powerful tests much more efficiently. And a practical takeaway of this result is that in the real world, auditors should be granted query access to predictive models, not just predictions on historical data. That's all for now. Hope you check out the paper and longer talk for more results and open questions. Thanks.